Okay, so I was uh, telling you that we meet at 10 past 11 and it is now 10 past 11. So we may continue with our discussion and all the other attending students may attend as they arrive. Now, the necessity of uniquely decodable codes was what we were talking about, and now I want to mention about the thing that I have promised and mentioned about very briefly a little bit earlier in the previous hour, and it was the Kraft Macmillan inequality. So for a code to be uniquely decodable, we need to have this condition. If we have for a code with n code words, okay, so in the alphabet we have n symbols with lengths L sub 1 to L sub capital N, okay? Then there is a symbol called craft number K of this code that is equal to I from 1 to capital N 2 to the power negative Li. So these lengths are in terms of bits, of course, 2 bits, 3 bits, 4 bits, etc. So they are 2, 3, and 4, this Li things I'm talking about. For all codes, summation of 2 to the minus Li will give you the craft number, and this must be less than or equal to 1. If it is greater than 1, it means that Li's are too small for the set. Let's quickly check from our previous example. Yeah, these codes, for instance. Let's look at code number 2. What are the 2 to the power things for these codes? Let me write in red. So this is 2 to the 1, which is, 2 to the minus 1, which is 1 over 2, right? Maybe I should write as 2 to the minus 1, which is 1 over 2. This is also 2 to the minus 1, which is 1 over 2. This is 2 to the minus 2, which is 1 over 4. And this is also 2 to the minus 2, which is also 1 over 4. And if you add them up, as you see, even these two will already make 1. And then these two will make 1 over 2. So 1 plus 1 over 2 is 1.5. This summation, the craft number of this code is 1.5, and it is clearly not less than or equal to 1. Therefore, it can't be uniquely decodable. So let's come back. This is necessary for uniquely decodable codes. This is the craft inequality, and the equality holds. Equality holds. Excuse me. For efficient binary trees. I would say trees, but it's binary trees. So, and that is the condition for efficiency. For example, this binary tree that I have drawn here, which is producing these codes, will make the craft number to be equal to exactly 1. So I'm pretty much sure that the craft number for this one would give you 1. Does it? Let us see. It's always a good idea to check scientifically. We have 2 to the minus 2. which is 1 over 4. Then again 1 over 4 for the second one, 1 over 4 for the third one, then 1 over 8 for the next one with 3 bits, then 1 over 16 and 1 over 16 for the last two. Now let's combine them. These two will make 1 over 8, and with this 1 over 8 it will make 1 over 4, and this 2 1 over 4 make 1 over 2, and this 2 1 over 4s will make 1 over 2. 1 over 2 plus 1 over 2 is 1. So this all will give you 1. K is equal to 1. Therefore, it's an efficient, let's say, Kraft vector, as they call in the notation. So if you make this kind of an efficient binary tree, not necessarily balanced. By the way, the balanced trees are also efficient. For example, if you have 0, 0, 0, 1, 1, 0, and 1, 1, these four symbols will have a Kraft number of 1, which means it is efficient. At least it's not redundant, in other words. Because with 4 symbols, it's always possible to have redundant codes. For each symbol, for instance, you may assign 3 bits, and then it will be obviously redundant because 2 bits is enough. Anyway, so this Kraft inequality is a check for you to check if more complicated codes are uniquely decodable or not, because sometimes you cannot see if something is the prefix of the other one, if it is uniquely decodable, can you draw a binary tree with that, etc. The possibility of drawing a binary tree is available to you if these lengths of the symbols will obey this rule. 2 to the minus li's summation must be less than or equal to 1, and preferably equal to 1. Now, for the equal to 1 case, now we have to look at some well-known techniques. And the first well-known technique that satisfies the Kraft vector is the technique in the class of techniques known as the Shannon and Huffman type coders. The name Shannon is due to his further collaboration, not only the information theory construction, which is an amazing invention by itself, but he's also collaborating with other scientists to literally come up with the Shannon type codes, also known as Shannon and Huffman type codes. Now, they come up with an idea. They are sparkled from the concept of one very important observation. And the observation is as follows. If L1, L2, up to Ln is a proper Kraft vector. So what do I mean by proper Kraft vector? It is efficient as well. It satisfies the equality to 1. It means it's a proper Kraft vector. Then, and of course, for n greater than 1, the non-trivial case, then Ln, the last vector's length, is equal to Ln minus 1, the one before that, for the efficiency. That is surprising, isn't it? I mean, it's, of course, possible to prove this, and proving this is also another exam question. Okay, always think of it like that. Prove that if it is a proper Kraft vector, then Ln is equal to Ln minus 1. And these proofs are rather tricky. You have to know the answer to be able to prove them. So making a research will greatly help. But ln is equal to ln minus 1 is an interesting observation. Let us at least see if our previous efficient codes really satisfy that property. Let's look at this code, right? Look at this. This is ln, the last length, which is 4. And ln minus 1 is also 4. As you see, 4 and 4. These two are the same as one another. Interesting, isn't it? Or let's look at this code 3, which is also an efficient Kraft vector, proper Kraft vector. The last one is length 3, and the one before that is also length 3. Now, that observation greatly helps us to construct our efficient binary trees. Now, another observation is also there. Again, if L1, L2, up to Ln is a proper Kraft vector, then L1, L2, up to Ln minus 2, excuse me, and Ln minus 1 minus 1 is also a proper Kraft vector. So I'm actually reducing one branch from the system, a shorter Kraft vector I'm coming up with, and its lengths are as follows. The last length is one less than this one. So if this is 4, for example, this is 3, and Ln minus 3 should also be already 3. And this is also a proper Kraft vector. What does that mean? And does it comply with our previous observations? Let's look at this again, binary tree. Here, this was Ln, this was Ln minus 1, this was Ln minus 2, okay, from the last. So Ln is gone, we don't have it anymore. Ln minus 1 is reduced by 1. Ln minus 1 is 4, minus 1 is 3. So instead of this, we replace it with a 3 length code word. So length becomes 3. And the one before that is Ln minus 2 is already with length 3, as you see. So these two will be combined to a single code word with length 3, which is the same as this length. And if you combine it with this one, two length 3 vectors are combined, this one and this previous combination, they will be combined to become length 2, which is the same as this one. Now, why do they happen? It's quite obvious, actually. When you look at it from the perspective of a binary tree, it's quite clear that if a binary tree farthest expansion is happening here, when you combine them, as you see, this combination will stop at this point, and it will be these two branches will be cancelled, and instead we will have only this branch, and it will stop at this point, which will have the same size as this one. Okay, that's how things work. Two branches are merged, and it will be the leaf of one previous one upper branch. And it's always coming, the last portions are always coming in pairs, because otherwise it means that we have 1, 0, for example, if the length of the longest one is this one. But if we don't have 1, 1, then it won't be an efficient code in a way. This will be very redundant. 1, 0, without any 1, 1 coming from here. Why? That would be redundancy. So That's why the last two are always the same length for efficiency. And when you combine them, you go up one branch, and then you become paired with another leaf here. And then when they merge, you come up with this point, which will be paired with this branch then. So everything comes in pairs because it's a binary tree. So these observations were critical, and they require some proper way of proving, rigorous proofs, which you can find. And I'm not sure if I will be doing that one, or maybe I will ask in a take-home examination to prove these observations. Actually, these are observations, but they are facts. They are true. They are, so they can be stated as theorems, which can be proven. Now, Huffman code is the first code that we will see, which starts from these two observations for the case of constructing. The alternative thing to this one will be called Shannon and Fano coding. And we will also see that. Huffman coding is a bottom-to-top way of constructing a binary tree. So how can we construct a binary tree from, let's say, n symbols? Let's say we have, so we are dealing with now Huffman coding. Suppose that we have A1, A2, A3, A4, A5, A6, A7. Okay, these 7 symbols. How can we construct a binary tree with these ones? Of course, by joining them in couples. So we have to merge the codes in the form of construction of a binary tree. Which two symbols would you merge first? Or how would you start merging? Let's look at our previous, again, the famous example up here. This one. The first merging one will be left deepest in the binary tree. They will be this one and this one. Okay. If I merge them first and then merge them later with others and merge others, etc., the other later merging ones will be having shorter code words, but the one that I have started to merge, this one and this one, they will have the longest code word, like this. So I'm starting with merging the ones that I expect them to have the longest code word. What would be a good idea for the last and longest ones? The ones with the smallest probability. So what I really do here is I sort according to their probabilities. So the smallest probability will be at the top, because from the top I will start merging, but it's just an illustration. That's not really how you do it. You don't have to sort. You can just find the smallest two probabilities and then merge them if you're writing a computer program. But for illustration purposes, this is PA1, let's say PA2, PA3, probability. By saying P, I mean probability of A4, probability of A5, probability of A6, probability of A7. Now, these probabilities, of course, they may be A1, probability of A1. I'm assuming that it's the smallest, but you have to sort accordingly, of course. Let's assume that A1's probability is the smallest, A2's is the next smallest, and the highest probability is A7, okay? So I just join them, these two branches, and I come up with a node. And the probability of this node is now the summation of these least probabilities, that is probability of A1 plus probability of A2. And I'm gonna call it probability 1. It's just a number, but those two probabilities are added. Now, you can think of that node as a root of or a symbol which denotes two symbols, PA1 from one side and PA2 from the other side. It's the combined combination of these two symbols. Now I will merge again, but before merging, I have to sort again. But this time the sort will contain P1, this one, and then PA3, PA4, PA5, PA6, PA7. So whichever is smallest will go up. And probably when I add PA1 and PA2, this P1 may be larger than PA4, let's say, something between PA4 and PA5. Then you have to replace the position of that in that place, and it will be, after sorting, something like this. Let me not use red, but another color. Let's use blue, for instance. PA3, PA4, and then P1 is here, and then PA5, PA6, and PA7. So essentially, it's the same as, excuse me, it's the same as this one. P1 came to here. And now I have to merge the two least probable things, which are, according to this illustration, PA3 and PA4, which will generate something else. And that something else I will call P2. Okay, maybe they will interchange their places and the ordering will be, the smallest will again be P1 after reordering. It will be P1 and then P2 and then PA5, PA6 and PA7. This P1 therefore goes to here and this P2 comes here. The others are just reflected as it is. And then these two are further merged to come up with P3, let's say. And then they must be reordered. I'm running out of space, so let me continue from the bottom side here. I have a P3, and then I have PA5, PA6, and PA7. Suppose that this is also the correct probability ascending order by coincidence, and therefore I have to join P3 with PA5 and say that this is P4 and the others just stay, PA6 and PA7. And when I order them, let's say that the new ordering is PA6, PA7, and P4. Excuse me. Here. So after this ordering, I have to join these things, and P4 comes here, by the way. And I will have a P5. It's a tedious process, as you see. Unfortunately, it's not P6, it's P5, like this. And then I have P4. Now, these are the last two entities, probabilities that we have. If P4 is smaller, you can put it up, or larger, you can put it down, but those will be the last to merge, so it doesn't really matter. So let us join them, and we come up with so-called P. Now, according to the formalism or the algorithm of Huffman coding, what kind of codes do we have eventually? We will just assign names to the upper going branches and lower going branches, and you can do it arbitrarily. To the up, you can say 0, to the bottom, you can say 1, or sometimes 0, sometimes 1, because it doesn't really matter which you call. But of course, while programming, you just choose one. Let's say that the up ones are 0 and the bottoms are 1. Like this. Then from this root of P, you traverse up to the leaves here. For example, since the longest one is that one, let us look at what is the code word for A1, which is here. To A1, for A1, it is as it continues as P1 and then P3 to P4. So it is in P4. P4 from P starts with a 1, and then P4 to P3, it's a 0. So first one is 1. Let me write it then. 1, and then a 0 here to P3. From P3 to P1, it's another 0. And from P1 to PA1, it's another 0. So the symbol, the code word for A1 is 1, 0, 0, 0. To PA1, I can clearly see that all the way up to this P1 was the same, and the last one is just another 1. So it should be 1, 0, 0, 1. Okay. How about PA3? What was the code word for that? PA3 was merged here with P2 and P2 with P3. And then P3 with P4. P4 is here. So it will be 1 for P4, 1, then 0 for P3, then 1, 1, 0, 1, and then 0. 1, 0, 1, 0 goes to PA3. And PA4 is 1, 0, 1, 1, because only the last symbol is different. 1, 0, 1, 1 is, excuse me, I'm just messing up with the orders. It must be like this. This is PA1, this is PA2, this is PA3, this is PA4. Now I will continue with PA5. PA5 has been merged with P4 here. So P4 is here with 1 for P4 and another 1 for PA5. So it is 1, 1. 1, 1. Quite small. Interesting. And then PA6. PA6 is here. Through P5, it is 0 and 0. This 0 and this 0. So 0, 0 is PA6. And PA7 is 0, 1, 0, 1. So these are the code words. 4 code words with length 4 and 3 code words with length 2. Is it a craft vector? That's interesting. I mean, just I was not expecting this kind of an output, but it must be correct if we didn't make any code assignment mistakes, which is very much probable. I do not trust myself in this aspect. Anyway, let us see if things work. 2 to the minus 4 plus 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 2 to the minus 2 plus 2 to the minus 2 plus 2 to the minus 2. What is it? 2 to the minus 4 is 1 over 16. And there are 4 of them. Plus 2 to the minus 2 is 1 over 4, and there are 3 of them. So it's 3 over 4. 4 times 1 over 16 is 1 over 4 plus 3 over 4. It is 1. I'm happy. That was a relief to see that probably I didn't make any mistakes for assigning the bits. But of course, after assignment ordering, I just made it randomly. You shouldn't do it that way. You have to find the summation probabilities. You must add up these probabilities, PA1 plus PA2, whatever that probability number is. According to that probability, you must insert it among the rest, like this one. I just assume that it is here. It may be down here or here or up here, whatever. And accordingly, you continue and continue and continue joining. And each joint will make a binary tree branch. A binary tree will have 2 branches at each node, and it automatically constructs the binary tree. That's what we do for Huffman coding. Now, Huffman coding is a very enjoyable algorithm, and people just love it. Therefore, in data structures courses in computer engineering, it is also a very commonly encountered algorithm. So it's very nice to know about it. But right now, apart from the algorithm, which is nice by itself, we are also looking at its approach to the compression scheme. Why does it compress? It compresses because of 2 things. Because it is assigning the longest bits to the least probable ones by construction of a binary tree, by first constructing the nodes from the least probable ones, but which will cause those leaves to be at the end of a longer tree. So they will have longer code word lengths. And since it is also constructing a binary tree, by construction, it is uniquely decodable. That's why it's very much preferable and people just enjoy it. And it is very efficient too. There are extensions to Huffman coding like adaptive Huffman coding as the streams come inside or as the data is streamed, the probabilities are adjusted and the code word assignments just interchange. That's an extension to Huffman coding. Or you may group symbols not as individual symbols, but you may group them into 4, into 8 symbol groups. And group-wise, you may try to assign a Huffman code for the group itself, which may be more efficient under some circumstances. So that's what Huffman coding is. And since it is very popular, as I repeat, you will be able to find examples of Huffman coding on the internet in a lot of cases. In the previous years, when Java applets could be run from browsers, internet browsers, there used to be a very nice animation of running the Huffman coding with all the 26 English letters and space, which is 27, and maybe full stop, which is 28. So every symbol that you may think of as a character may correspond to a new symbol. and they have their probabilities for a long text, and that long text is animation-wise encoded. First, the Huffman tree is constructed, then these code words are assigned, and then a new message comes in, which is encoded using these. So if you just write these codes side by side, you should be able to decode them very easily. And how do you do that? Let us see that one as the last thing for today. For instance, the stream that we have, let me write in green, is like this. 1, 1, which corresponds to PA5, by the way, then 0, 0, which is A5, and then A6, and then 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, and 1, 0, 1, 1. Now, if you look at it, it looks pretty much messed up, right? How can we decode this? We don't even know which one corresponds to which, but actually we do know it. This thing is instantly and uniquely decodable, this sequence. And it is done like this. You start feeding this side from here, from the root. You start pushing the stack. What is it? It is 1. So it goes to P4. Okay. And then comes what? Another one. So from P4, we push another one, which is 1. And then we arrive at a symbol. Therefore, we cut it from there. It's a symbol, PA5. And we decode it. As soon as we decode it, we cut it from there. It's decoded. It is A5. And then we start pushing from the top as well. Again, is a 0. That 0 will arrive at P5. And another 0, it arrives at PA6, which is a symbol by itself. So we stop. And we cut, and we say it's A6. We don't continue any further. Then, again, it starts with a 1, so it arrives at P4. P4 is here. And then it continues with a 0, so it visits P3. P3 is here. It continues with another 0. It goes to P1. P1 is here, all the way here. And it continues with another 1. Only then it arrives at PA2. So we cut it now, which is A2, like this. So as you see, as soon as you detect a symbol, cut, and you release that symbol. And then for the rest, as soon as you detect a symbol, you cut, and you release that symbol, which is very nice. That is the magic of construction of binary trees, the decoding strategy. And interestingly, on the long run, if your sequence is, let's say, approaching to size of infinity, then this Huffman coding can compress asymptotically down to the entropy of the sequence. So it will be as efficient as possible for infinite extent sequences. But for finite extent, it will not be very efficient, maybe, I don't know. And the inefficiency of such algorithms in terms of computer programs, we have to think about computers to decode, to encode and decode these things always. It will not be very efficient for shorter sequences because of several things, including one very critical observation, which is the unawareness of the decoder regarding this so-called code book. This is a code book 1000 to represent A1. We didn't know that. And the decoder may not know it too. So how can you let the decoder to decode according to this code book? By inserting a header into the file, which indicates first the code book at the header part, and the rest is the encoded bit stream. So there is an overhead in terms of a header, which indicates what is what. That is a handshaking protocol. Like, which language am I using to communicate with you? I'm using this language, this code book language. So I have to tell you the language first by transmitting this information or putting it in the header size, which will enlarge the data first a little bit. And after that, by efficiency of these things, more and more efficiency, it will tolerate first for the overhaul of the uh, the code book, the overhead of the code book, and then it will be more and more efficient. So usually in practice, you will notice that small files will not be able to compress using, let's say, zip. If you have a very small, tiny little file, if you try to zip it, it won't be compressed because of the headers and the inefficiencies yet. Because that small file could also have, by coincidence, this A5 and A6 and A7, which are, sorry, excuse me, A1 and A2 and A3, which are length 4, and A4, length 4, which is inefficient actually because there are only 7 symbols. So it would be enough for me to represent everything with 3 symbols, everything, all of them with 3 symbols. But now I'm using 4 symbols for some of them so that I can use 2 symbols for the more frequent ones. Okay, that's a compromise. And if these 2 symbols, 2-bit symbols are more frequently encountered, of course, it will be more efficient. But if by coincidence you come up with these longer symbols, then it will be even less efficient, of course. That's why usually small files will not be able to get compressed using this lossless compression methods, including this Huffman coding. We will see another code which is called the Shannon-Fano code next week, and then we will continue with the essence of zip type of compression, which is also, in a sense, constructing a code book. And the construction of the code book very much resembles the binary code generations in terms of idea, but seeing the binary code, binary tree generation in Huffman coding is very obvious. This whole thing is a binary tree. In Shannon-Fano, we will construct again another binary tree, which is another way of approaching this one, but not from merging, but instead splitting. So it will start from the top and it will split into the binary tree. That will be the Shannon-Fano code that we will see. The others, well, they are more like dictionary-wise construction of a code book, which is a little bit different, but we will also see those things. So I think the time is okay for the time being. So I will stop. But since I didn't let you ask questions in the first lecture, but at the end of the first lecture, I can ask you if you have any questions now. These are very popular things. Please go to the internet and look at the illustrations, look at the explanations. You will find a lot of excellent explanations regarding this Huffman coding, by the way. But anyway, if you have any questions, I'm listening.
I want to ask you about the authors of the books,
Yes.
reference books.
Oh, yeah, the ones that I mentioned in the first lecture, they were David Solomon. I can write them.
Okay, David Solomon, I wrote it.
Uh, yeah, David Solomon. And the other one was Khalid Sayud. these guys.
Okay, thanks. What about the recordings?
What about the recordings? I don't know.
Uh,
What about them?
no, where can we find them?
uh, I'm not sure whether you will be able to find them or not, because I haven't decided whether I should put them on the internet. Because when I do that, I usually put it on YouTube and it will be freely available. Well, I will check if I find it not terrible, if I find them appropriate enough, I will put them on the YouTube on my YouTube channel with my name.
Okay, thank you.
Hmm. Probably I'll do that, but it takes time usually. It's a slow process to uh, process the YouTube and upload some large videos like these ones. These are long, unfortunately. But yeah, I will do that. Okay, I will put them on YouTube under my YouTube channel, where right now you'll be able to find some signals and systems courses and image processing courses from there, and this will also be there. Okay, I will do that.
Okay, thank you.
Right, any other questions? Probably no questions. Then I'm ending the lecture right now. I'm stopping the recording.